In this lesson, we're going to take a look at functions that are not differentiable at a point. Now, this will help us to better understand the derivative of a function, because it's not enough just to understand when a derivative exists. We also want to understand when they don't exist and why. It's also going to be important because, as we'll see later on, we'll need to identify when derivatives do not exist when we're analyzing the graphs of functions. That's going to be an important point of determining where a function is increasing and decreasing, or concave up and concave down, which we'll get to later. Now, before we start looking at examples of when functions are not differentiable, let's quickly recall what it means for a function to have a tangent line at a point. So take a look at this graphic down here. We've seen this before, but let's just review it. We have here the graph of the function y equals x squared. That's the blue curve. And right here is a point where we want to identify the tangent line at that point. Now we have what looks like a tangent line, which is the red line right there, and that is the tangent line. But the most important thing to note about that line is the following. Notice that when we zoom in around this point, we will not be able to see any difference between the graph of the function y equals x squared and the graph of the tangent line. So if we zoom in, you see eventually the line and the graph of y equals x squared merge into one graph, and we can't really see the difference between the two. Now, if we were to take that line and tilt it just a little bit, that line does not look like its tangent. And notice if we zoom in at that point, we will always be able to see a difference between the line and the graph of the function. No matter how far we zoom in, we will still be able to see a difference. So that line is not tangent. So that's what it means for a function to have a tangent line at a point. Now let's take a look at some examples of when functions are not differentiable. And remember, the key thing here to remember is that the derivative is the slope of the tangent line at the point. That's what the derivative is measuring. It is the slope of the tangent line. Okay, now let's look at some examples of when functions are not differentiable. So in this example, we want to show graphically that the function f of x equals the absolute value of x cannot have a tangent line at 0, 0. And so if it doesn't have a tangent line, then it can't have a derivative at 0, because the derivative is supposed to be the slope of the tangent line. So if there's no tangent line, we can't have a slope. So the derivative can't exist. So we'll look at that graphically, and then we're going to verify that analytically, that f of x equals the absolute value of x cannot be differentiable at 0. So here is the graph of the absolute value of x. Now the blue curve here, that's the absolute value of x. And the gold dotted line here, those are just some lines that we're going to try and understand why they can't be tangent lines. So we're going to try to fit a tangent line here at that black dot, but we're going to see that no matter what line we put here, that it can't be tangent. So let's do this. So you want to try to find a tangent line at that black dot. So you might try a few lines. Suppose we, maybe we'll try this one here first. Alright, so perhaps that could be a tangent line. Well, but the problem is, if I zoom in at that black dot right there, you notice that I do not completely cover the graph of the function. There's still a piece of the function over here which is not being covered by the gold dotted line. So that can't be a tangent line. So you might try, perhaps we could try this one, perhaps lean it this way. Well, but we still have the same problem. If we were to zoom in, if we zoom in near that black dot, we still are not covering the entire graph of the absolute value of x. Well, maybe we could try this one for a tangent line. What if we try to sort of split the difference and make it horizontal line right there. That's just the line y equals 0. Well, you can see if we zoom in at that point, we are not covering entirely the graph of the function. So at that black dot right there, the absolute value of x, it does not have a tangent line. No matter what line we try to fit through that black dot, when we zoom in, we are not going to entirely cover the graph of the function. So this function does not have a tangent line at 0, 0 for that reason. Now let's verify analytically that the derivative does not exist. So we have to go back to the limit definition for the derivative. So what if we tried to evaluate f prime of 0? We'll go back to our limit definition. And substituting the absolute value of x in for f, we get this. Alright, so we have to try to evaluate this limit. Well, this limit is not going to exist. And let's see why. Well, if we look at the left and right hand limits of absolute value delta x over delta x as delta x goes to 0, we get the following for each. And so we see the limit from the right of absolute value delta x over delta x is going to be 1. And that's because as delta x is approaching 0 from the right, it is a very small positive number. So the absolute value delta x is just going to be delta x itself. And of course this quantity is always equal to 1, and so the limit is 1. Now if we look at the limit from the left, well, the limit from the left is going to be negative 1. And that's because if delta x is approaching 0 from the left, then delta x is a very small negative number. Now remember, the absolute value of a negative number, like negative 3, that is actually negative of negative 3, which is positive 3, right? So if I want to get rid of the absolute values here, since delta x is a negative number, the absolute value is going to be negative of delta x, because negative of a negative will make a positive number. And so you see this quantity is actually negative 1 all of the time. And so the limit is going to be negative 1. Well, you see my left and right hand limits now, they are not equal. And so therefore the full limit does not exist. And so therefore, going back to the derivative, that means f prime of 0 does not exist. And so the moral of the story here is that anytime the graph of your function has a point or a cusp, that means that your derivative at that cusp is not going to exist, because your left and right hand limits of the derivative will not be the same, or they will not exist. And so the full limit cannot exist, and so your derivative does not exist. All right, let's take a look at another example. So we're just going to look at this one graphically now. So let's demonstrate that f of x equals the cube root of x has a tangent line at 0, 0. It does have a tangent line, but the derivative at 0 does not exist. And let's try to see why. What's happening there? Well, here's what the graph of the cube root of x looks like. It's the blue curve right here. Now, if we try to construct a tangent line right there, now remember the tangent line is supposed to be a limiting position of secant lines. So here we have a point up here on the graph of the cube root of x, and we're going to let this point slide towards the point at the origin 0, 0. And let's see what happens to these secant lines. What are they becoming? All right, now also keep an eye on the slope of the secant lines. Currently our slope is 3.66, and let's step this point in a little slower towards that point and see what's happening to the slope of our tangent lines. So we see that the slope of our tangent lines is getting larger and larger, and it looks like our secant line is actually becoming vertical. And that's exactly what's happening. Try to step that in a little faster. All right, yeah, so you see what's happening now is the secant lines are becoming vertical. The slope of the secant lines, they're getting larger and larger. They're going to infinity. And the derivative is supposed to measure the slope of your tangent line. Well, so we see the derivative cannot exist at 0 because our tangent line is vertical. So while we do have a tangent line, the derivative does not exist. Let's take a look at another example. So here we have a function, piecewise defined function. F of x equals x squared for x less than or equal to 1, and x minus 1 for x greater than 1. Now here's what the graph of the function looks like. And you notice that we have this break discontinuity at 1. For that reason, this function is not going to be differentiable at x equaling 1. And to see that, let's look at this other graphic down here. Now you remember that the tangent line to the graph of a function is supposed to be a limiting position of secant lines. So if we create some secant lines on this graph down here as follows, let's see what happens. So here we have a secant line, right? There's the point, our base point, and we move off to the right a little bit and put another point on the graph of our curve, and we draw a secant line. Let's see what happens to the secant lines as we let this point here move along the curve in that direction towards x equaling 1. Now, one other thing here, this little line segment right here, that's actually not part of the graph of our function. That's just a little glitch in the computer graphing system. So let's see what happens to the secant line. All right, well, you see as that point moves along the curve, our secant lines are becoming vertical. A vertical line does not have a slope. The derivative is supposed to be the slope of a tangent line, so the derivative cannot possibly exist at x equaling 1 because of that break discontinuity. All right, so the moral of the story here is that whenever your function has a break discontinuity, your derivative cannot exist, or any type of discontinuity for that matter. So we have a general rule we can follow. If the graph of a function has a cusp at a point, c f of c, then f prime of c will not exist. If the graph has a break discontinuity, or in fact any type of discontinuity at x equaling c, then f prime of c will not exist. And if the graph of a function has a vertical tangent line at c f of c, then f prime of c will not exist. So there are 3 cases when the derivative will not exist. So that concludes our discussion of examples when the derivative of a function will not exist.